Hello, everyone. Today I'm going to present our work while at USC, where we developed an end-to-end system for federated learning workflows called MetisFL. This is a long-year effort and through many collaborators at USC, and this work was basically conducted with the help of Valandis, Patrick, Armagan, and Jose Luis Ambide. Okay, I'll start briefly by, of course, everyone is familiar with federated learning concept, but why so important? So federated learning is very important because right now, till the advent of federated learning, most of the consortia or federations that were formed had to share their data. However, recently many different data regulation frameworks have been enacted, like the GDPR, CCPA, and more recently also the new Federal Act on data protection on Switzerland. So the core idea of federated learning and the core concept is that when you have different edges or different nodes or silos that they want to train and join model, traditionally you were sharing the data. Right now you need the data remain at the silo, and what's being shared is only the locally trained model parameters. To dive a little bit deeper, what is federated learning? Federated learning consists of multiple silos, sites, many different names have been assigned, like clients and learners. Here you can see 3 hospitals, with each hospital having its own private local data. And this data never leaves the site, and what is being shared is only the locally trained model parameters with a centralized entity that is called the controller or aggregator. The federated learning concept can be applied on different machine learning algorithms like neural networks or traditional statistical analysis tools. So in a typical federated learning training, on the right-hand side, what I'm showing is a slightly small pseudocode where there are across different timestamps, assuming we have a controller and participating clients and learners. On the first time, the controller is sending or dispatches the training task, and this can be seen also between the timestamps T1 to T2. Then, for every client in parallel, what's being done is between the timestamps to T2 to T4 is every client in parallel trains a global model, and upon finishing or completing the local task, it sends the local model back to the controller. Thereafter, something that is being also slightly overlooked by previous works is that the controller needs to take all these models, insert them in memory or on disk, select the models that needs for the aggregation, and perform the aggregation in order to compute at timestamp T7, the global model. Once the global model is computed, then it's being dispatched to the learners or a selection of the learners for evaluation. And at timestamp T9, you get the result of this evaluation. This whole pipeline from T1 to T9 is also known as the federation round. Here today, we're going to also discuss a bit on the different learning frameworks, and I'll start by showing our learning framework that we built at USC for research purposes. MetisFL consists of a federation driver, which is responsible to orchestrate and decide what will be the federation that is going to train the model. Then there's a federation controller, which is developed in C++, and that's the core and the key component of MetisFL that consists from different smaller modules like the model aggregator, the secure aggregator, the model store, the evaluation task scheduler, and the client selector, for instance, also. And of course, the component that's called the federation learner. At its core, the MetisFL is developed with the gRPC point-to-point communication, and is uses fully homomorphic encryption to perform secure transmission and aggregation. On the next slide here, what I show is a typical workflow. So assuming you have a user, the user defines a YAML file, and then the federation driver reads the YAML file in order to send it to the different respective participating parties. The first participating party is, of course, the controller, which is going to run a containerized version or a VM, and then to every other learner that's going to participate in the training. You can see here with the different boxes the workflow. So starting from point 1 up to point 8, how the work is being executed. So once the YAML file is defined, then the driver initializes the control learning processes. On step 3, the learner is registered with the controller once they started, and the controller selects clients to train the machine learning model on step 4. Thereafter, the select client, step 5, the clients are selected for training, then perform the model aggregation, which can be performed with or without secure aggregation, which is optional. And then once the aggregation is done, then we select the clients for evaluation. To dive a little bit deeper, what are the MetisFL key features? At the very beginning, we said that the controller is a C++ implementation. The reason we did this is because the original prototype was developed in Python, and we saw a lot of delays in terms of when it comes to consider multiple learners, multiple clients in the federations. And the reason we wanted to have this implementation is we want to have more better thread memory management. And one of the core ideas also is that the controller is performing all the dispatching and evaluation, all the dispatching of training and evaluation tasks in a synchronous manner. So it doesn't wait for an acknowledgement back from the clients, but submits the acknowledgement back, submits the task at the training or evaluation in a synchronous configuration manner. The reason we're doing this is because on the prototype system we saw a lot of delays when it came to how to scale the controller to consider multiple clients or learners in the federation. Another component is the parallelized aggregation. This is also, again, part of the C++ implementation, and the reason is that we wanted to make sure that we saw also later with different actors when we conduct different evaluations that by enabling this parallelized aggregation, by having better thread management and leveraging all the cores in the machine, you can actually have 10 times and 100 times faster aggregation compared to other systems. And finally, one more component that is critical was the model exchange optimization. So instead of as other systems send the machine learning model to be trained as a single let's say message, here what we're doing is we're flattening the entire model into a sequence of a federated model, the model, and then in a sequence of messages, and every of variables, and every variable consists either just is a plain text or cipher text variable tensor. And one more critical thing that other systems have overlooked is how the different data types that you need to consider. So you might have a machine learning model that is trained with a float 32 or a float 8, but then during transmission or they actually being converted back to float 32. So here, what we're doing also, we are enforcing that whatever precision you want to preserve, that's also being communicated throughout the network. Of course, MetisFL is not the single system that there is out there right now. There are many different systems like Fate, FedML, Flower, FetchScale. What we're showing here is that there is a thriving ecosystem of different open source frameworks. Each framework has its own different license, has different use cases, and is different focus. The focus could be more on production, could be more on research, could be more on industrial settings. So each framework has its own flavor. And for that particular reason, we perform two evaluations. One is in terms of qualitative and one in terms of quantitative. In particular, in our evaluation in this work, we compare against the NVIDIA Flare, Flower, FedML, IBMFL, and OpenFL. And in this qualitative evaluation, what we show, there are different dimensions that we consider. One dimension was in terms of deployment, basically whether the FedML framework can be supported on a standalone setting or can be done as a distributed training or distributed in distributed fashion. There's also whether the framework can support cross-silo, cross-device, and of course containerized execution. Thereafter, there is a dimension based on the machine learning environment. So what is the backend of the machine learning training pipeline? It could be TensorFlow, Torch. Other systems like Flower support more, and NVIDIA also supports for SAS9. Then you have the data partitioning. So in terms of whether the data that has been whether the framework actually allows training on data that are being horizontally or vertically partitioned. In terms of private security, we consider whether you have whether masking or full homomorphic encryption is being used, or other, and what is the type of the cryptographic library in the system. And last but not least, we have the different communication topologies like centralized and decentralized, and finally the communication protocol, whether synchronous or asynchronous. One critical thing that we observed during our evaluation is that our system supports asynchronous protocol communication, whereas other systems were still focusing on the synchronous approach. And of course, there's a software based on the software type. Most of the systems out there right now, they are on Python. Others that are using Python or Go, for instance, Substra, which I don't have in this analysis, but in our case, we have Python and C++. Then in the more interesting quantitative analysis, so again, to do this minor recap, from T1 to T9, we show the federation round. And as you can see, in the plots below, we evaluate the different frameworks that we saw earlier, except from OpenFL, with respect to the with respect to the different set of operations. So the idea here is that we wanted to evaluate in a micro setting how much time does it take for every system in our evaluation to do the dispatch of the training, the actual training of the global model, and basically training and send of local model, train the global and send the local, which is basically the training round, and then the aggregation and the evaluation round, which consists of dispatching and evaluation. We don't consider the insert and the select operation. We consider them as constants in our setting, since all the models were fit in memory. For our benchmark, we're using a multi-layer perceptron with 100 densely connected layers, which we shrink and increase and shrink based on different number of parameters per layer. So for the case of 1 million, we consider 100 parameters per layer across the 100 hidden layers. And for the 10 million, we consider 320 parameters per layer. As you can see on the evaluation, we observe that for the different systems, the MetisFL is 10 times and 100 times faster, almost across all operations. Nevertheless, the one that had a very consistent behavior in this evaluation was the flower. And we see that as the number of learners on the x-axis, sorry, I didn't explain this, but on the x-axis we show the number of learners, and the y-axis is execution, is latency or time, wall clock time. And the flower framework is the one that has the most consistent behavior, is linearly increasing. The latency is linearly increasing with respect to the number of learners, whereas other frameworks, for instance, other frameworks, I don't see them here, but basically other frameworks fail to perform some of these operations. This happened actually on the 10 million parameters. For instance, on the federation round, we couldn't, the NVIDIA Flirt failed when we considered 100 and 200 learners, so we could not actually perform or conduct evaluation on NVIDIA Flirt. Overall, this is the first time that this type of micro analysis on the different operations that are performed throughout the federated learning training workflow is done. And we show that by performing a better implementation or better re-engineering of the federation controller, you can actually accomplish much more robust and more improve the execution flow and the execution time overall in the federated learning training procedures. As part of our future work, we want to extend this stress test of the different benchmarks across different FL systems when we consider thousands of millions of clients, for instance, for the cross-device settings. We also need to consider training with very large or extremely large models. For instance, you might have some LLMs and you want to basically perform some aggregation of the different layers of the different, or you might have a visual transformer with million parameters, and you want to test that in a federated setting. But also we want to analyze the synchronous and asynchronous training workflow. One more instance component that we want to analyze is the backend. So the idea of having different models but the idea of having the controller storing the models on a different, like a Redis or on disk, and then see how that storage affects the overall execution workflow. Finally, we want also to perform the similar analysis as we discussed in this presentation with respect to different security protocols like full homomorphic encryption or multi-party computation. And hopefully I'm on time. Yes.